Hello again. We are in Topic 6, Lesson 3. Open your books to page 123. 123. Practice 6.3 is posted in Schoology and it's due in Ask Your Teacher. But here's my recommendation. If you're at home sick or if I'm absent or your teacher is absent and you're watching this, then just do the assignment once to finish the video. It's that easy. Okay? You will need a Lesson 3 adjustment sheet. That is hopefully going to be given to your teacher or posted in Schoology. But if you're watching this video, I wouldn't worry about it too much because as I go through and do the notes for this lesson, just make the adjustments in the book. So just follow through in the book as I do. I did post it on this next page, so if you would like to see it and if you would like to print that, that's fine. Might be posted in Schoology, whatever. Okay, so here we go. So we're going to be using on this problem, we're going to be using what we just used in lesson 2 about exponential function. So remember an exponential function. Let me go back a page and just refresh your memory. An exponential function, f of x or y, is equal to a times b to the x. A is the initial amount. B is how is it changing. Okay, so what is its ratio? Okay. So, Cindy is buying a new car and wants to learn how the value of her car will change over time. Insurance actuaries. Okay, so I'm going to stop for just 1 second right here. Insurance actuaries. What an insurance actuary is this is a profession that many people that are good in math go into. Actuaries. Now, it's not an easy profession. You a lot of times get a math degree or maybe a degree with statistics, and then you become an actuary and you have to set for tests. The reason I'm telling you about that is because this is a pure math occupation. And what insurance actuaries do is they predict the future value of whatever or of how much the cost is, but they look at the data and they predict. So it's a really good field for people who are great at math. It is not an easy field, so you do have to sit for tests, and don't be surprised if you sit for the test, you don't pass it the first time. But again, just want to tell you there is a math occupation you can go into. Okay, so one such function is applied to the car whose declining value is shown at the right. Describe how your value of the car decreases from year to year. So look at how the car depreciates from year to year. From year to year, okay? Is it going down by the same amount? If it's going down by the same amount, we know that it's going down, right? I didn't spoil that for you. It's going down by the same amount, then we know that that would be a linear function if it's going down by the same amount. If it's not going down by the same amount, see if it's going down by a ratio. So pull out your calculator right now, and on your calculator, and we always want to take the second value divided by the first one. So we're going to take 8,520 divided by 10,000. So do that right now on your calculator. 8,520 divided by 10,000. And do you get a funky number that looks like I got 0.852? Okay, so let's see if it's doing that same thing here. So now this time, you're going to take 7213 divided by 8520. So 7213 divided by 8520, and we get 0.8465. Okay, but pretty close, pretty close. Okay, then 7213 divided by 6100. Okay, I did that wrong, didn't I? You always have to take the second value, divide it by the first. So 6100 divided by 7213, and we get 0.8456. Those are all pretty close together. So what kind of function do you think this is? Okay. Oh, this one I'm supposed to say that it's going down or decreasing, and it's going down by a ratio. Then what kind of function would this explain this type? This would probably be an exponential function. It's not exact, so we might have to have a little more information. It's probably an exponential though. Okay, I know it's an exponential. Now, given your answer to part B, what is needed to find the function the actuary is using? Well, keep in mind we're using the function y equals ab to the x. So we would have to know the initial amount. Yay, we have that. Then we would have to know the ratio, okay? So the actuary would need to find the ratio, which we kind of already found for them. Okay, the constant ratio for the declining, what is the constant ratio? I'm guessing it's about 0.85, something right around there, approximately that. And they would be able to do some more with that. They have more training. Okay, good. So this is an application that you can see and a career that you can actually see for math, and so I wanted to point that out. So this is not in your book, what I'm telling you right now, but I would strongly suggest that you write it. And I would turn to page 126. And so on page 124 in the left-hand column, okay, we're going to put some information pretty soon, this information down here, okay? So let's read the problem so you kind of see where we're going. The population of Hillville grows at an annual rate of 15%. What will be the estimated population of Hillville be in 5 years? So what is happening? This is a population, and the population is growing. So this is what is called an exponential growth. So you want to put this over in the left-hand column, and you want to put this in the left-hand column. F of x is equal to a times b to the x, where a is greater than 0, b is greater than 1. It looks like that. That should look familiar. But an exponential growth function, okay, is going to look like this, where we have f of x is equal to a. That's still the initial value, but now instead of b, okay, this becomes your b. B is the same as that. But now what happens is this is going to be the growth factor. Okay, r is the growth rate. And 1 plus r, so 1 plus the rate, because it's a growth, it's going to be a plus. It's a growth, so it's going to be a plus. You'll see later on what we call a minus. So the growth factor is 1 plus r, which used to be b. So this now becomes your growth factor. Okay, and this is the equation we're going to use. So let's do this problem. So write this down. Exponential growth function. The growth factor is the 1 plus the growth rate. So put this in your note. Pause if you didn't already get it. So now that you know what a growth factor is, or you've written it down, let's write it for this exact problem. So let's read the problem again. It is a growth, and it happens at a rate of 15%, and our initial population is going to be 5,000. So remember our function, f of x is equal to a times 1 plus r to the x. So a is still the initial amount. So our initial amount here is going to be 5,000. Then we have 1 plus the rate. Now you'll remember, if I have a percent, I have to change it to a decimal. So if my percent starts, my decimal point starts here, remember a percent always looks bigger, okay? Decimals and percents are equal, but a decimal always looks smaller, percent looks bigger. So it's going to be 1 plus 0.15 and then to the x power. That's what your function is going to look like. So this is your growth function. Now we would simplify this, and we would write it like this. And if it's going to be a growth rate, it's always going to be bigger than 1, so you're always going to have a 1 right there. Keep that in mind. Good. Now this one is in your book, and it says the population of Valleytown is also 5,000, with an annual increase of 1,000 people. Can the expected population of Valleytown be modeled with an exponential growth function? Explain. Well, okay, this problem is weird. We'll discuss the weirdness of this in just a bit. But see how it increases by exactly 1,000 every year? So this is a linear function. Linear function. Because it increases by an amount, not a ratio. It's a set amount. Okay? Okay, let's just talk briefly about the weird one. Why are they adding 1,000 people every year? Exactly 1,000. Does anybody else find that weird? Yeah, okay. So just pointing that out. How would we know exactly 1,000 people are going to come into your town every year? Okay. Now we are skipping example 2. Don't worry about it. You're going to be fine. There's a reason I'm skipping it. And we're going to actually jump down to example number 3. but this could go in the same place. Yeah, just put this information like in example 2 or example 3 space on page 124. And what this one is talking about is exponential decay. So exponential decay, you can imagine it's going to go down. So remember when we were doing functions yesterday or last lesson, and we had some that would go up and some that would be down, going decreasing and increasing. So if it's an exponential growth, it's going to go up because it's increasing. If it's an exponential decay, it's going to come down. So this is a growth and this is a decay, and it makes sense. Okay, a growth is going to, as x increases, y increases. A decay is x increases, y decreases. Okay, so that makes sense. So an exponential decay is where a is greater than 0, so we have a non-zero, but now b is going to be between 0 and 1. A decay factor is 1 minus the decay rate. So now this a stays the same, but 1 minus r is going to be your decay factor. This is the factor, where r is the decay rate. So r is just a rate, but 1 minus or 1 plus is going to be the growth factor of the exponential. So hopefully you've written this down. We're going to do this example. It is part of the sheet that I gave to you, but if not, you can just adjust example 3 to go along with this. So if you are at home, you don't have the sheet, you can adjust example 3, and I'll show you how to do that. Okay, so this is example number 3. It's the bottom of page 24. If you were at home, you're just going to make adjustments. First off, okay, this is example 3. Okay, and I left off decreases by 20%. That's in your book. The only adjustment, if you're at home, that you need to make is cross off the question they ask, which is in how many days will the number of views per day be less than 1,000, and we're going to change it with how many views will there be in 7 days and how many views will be there in 10 days, okay? So this is a problem we're going to do now, so you can do it on page 124 with these adjustments. So the first thing we have to do is we have to write the function. This decreases by 20%, so this is going to be a decay because it decreases. So we're going to do f of x, and remember decay is going to be a times 1 minus r to the x, where r is the rate, okay, that's at 20%, and a is going to be the initial amount. So let's fill in what we know. We know that the initial amount is 8,192. We know that the rate that it decreases by is 20%, but we have to change that to a decimal, so we move the decimal point, so it's 0.20 to the x. So our equation is 8,192 to the 1 minus, that's going to be a 0.8 x. So this is a function we're going to use. First, we're going to do it for 7 days. We're going to do it for 7 days. So we're going to find f of 7. Okay, so we go 8,192 times 0.80 to the 7th, because our variable, okay, what we're plugging in is going to be our exponent. Pull out your calculators. Here we go. So when you plug that into your calculator, you got 1717.98 blah, 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 blah. Okay, so we would say that in how many views will there be in 7 days? About 1,717. About that. We're not going to come up with exactly, okay? If you forgot how to do it, I'll tell you on the f of 10. So now we're going to find f of 10. Oh, wait, but remember, it's a fan favorite if they have at least 1,000 views. Do they still have 1,000 views? Yes, they do. So it would still be a fan favorite. So now let's do it for 10 days. So we do the same thing. We're going to plug in 8,192 times 0.80 to the 10th, because we're finding f of 10. Okay, so if you forgot how to do this, I'm going to tell you how to do it with your calculator. You take 8,192 times 0.8, and then you're going to hit the tenth, okay, what looks like the tenth, okay, and to the 10th power. And you're going to get 879.6, blah, 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 okay? So this one would say would be about 880. Oh, so then this would be 1718. Okay, but anyway, this one's a fan favorite. Is this one a fan favorite? No, it is not. But that's how we use a decay function. They're going to tell us information. The one in the book, I'll show you later on how we're going to do that using Desmos. Okay. This is one where we're replacing both example 4 and example 5, so you can use all of that space on page 125 up at the top to talk about this problem. So Rich is comparing the cost of maintaining his car with a depreciating. That is a very common decay. Depreciation. And a car depreciates it as soon as you drive it off the lot of the car. When will the cost and the value be the same? So the cost is the maintenance cost. Unfortunately, the maintenance cost keeps on going up. It's an increase, so this is a growth. So we're going to write a decay for the value, and we're going to write a growth for the maintenance. Write an exponential growth and decay equations or functions to model this. So let's start with the value. So this is, I'm going to put v of x, just so we know this is going to be the value function, and it decreases, so this is going to be a decay. So we have the initial value. Okay, so remember, f of x is equal to a times either 1 plus or minus the rate. So if it is an increase, if it's a growth, it's going to be a plus, and if it's a decrease, it's going to be a minus. Okay, so keep that in mind. This one is going to be a minus. So my initial value is 20,000 times 1. Because it's a decay, I'm going to subtract my rate. I believe that says 15%. My rate is going to be 15%, so 0.15 to the x. So that's 20,000 times 0.85 to the x. That is my value of my car. Okay, it's going to every year go down by 0.85. So now let's do the maintenance. We're going to call this m of x. And this one is going to be a growth. So I'm going to take, the cost is initially $500. Then it's going to be 1 plus 28% per year. Oh my gosh. Okay, so that cost is going to keep going up. So we're going to take, and we're going to add 0.28 to the x. So this function is going to be 500 times 1.28 to the x. Wow, maybe buy a different car if it has that much. Read your consumer reports and find a better value if it's going to be a cost of 28% per year. Okay, so anyway, these are our two equations. Now what I want us to do is I want us to actually find out, when will this be the same amount? Okay, so we're going to go out to Desmos right now, and in order for it to be the same amount, where's it going to be the same amount? That's right, it's where they intersect. So we're going to go find out where they intersect approximately. And how many years will that be the same? Go to Desmos.com. So we are now on Desmos.com, and let's see. Oh, that's right. My marker doesn't work out here. So anyway, look up at that top bar where it says Desmos.com, and then you can, that's what you're going to do if you haven't already figured out where to go there. Okay, so let's put each of these functions in. I'm going to use y again just as faster. So the first one I'm putting in is the value. Y equals 20,000, and I'm going to put parentheses because I don't have a different way. I guess I could have said times. Let me see if I can. Times 0.85, and remember, use this A to the B button right here and put an X in. Now it graphed. Oh, mine is way far out. Hold on a sec. So I had to scroll out. Remember to scroll out on these. Just move your hands in and out. Okay, not on the graph. So that's what I did. So there's my value one. And you can see that car is going to depreciate pretty fast. However, not that fast. Because look, in 40 years, it still has some value to it. So just to let you know that. So don't worry about it too much. But maybe only $20. Okay, so now let's go to the next function. And we're going to have y equals 500 times 1.28 to the x. Okay, now we are going to have to play with this and see where they actually intersect. We're going to have to go way up here, and then we're going to have to stretch it back out. Okay, where do they intersect? Keep going, keep going. Ah, we're getting close, we're getting close. We're just going to keep scrolling until we find it. Okay, and then we're going to have to find out what that point is where they intersect. It's getting really close. So I kept scrolling till I got about right here, and then I said, look how close these are. Okay, and I'm just going to go up with that, and it looks like it's really close right there. Then I have that point, and notice I'm just taking my finger and I'm dragging it up. It looks like it's about 9 years. I'm going to say 9, okay? Because it's just getting closer and closer, but look what those numbers are, okay? Oop, yep. I'm going to say about 9 because that looks like about as close. So I'm going to say that it's 9 years. But what I wanted you to do is I wanted you to see how you could find that answer with using your graphing calculator of Desmos. Because remember on your EOC, you can use Desmos. So know how to use that. You can scroll out and just I'm taking my finger and I'm pointing on it and that point showing up and then I'm just going, I'm going to say it's about 9 years because it looks like they're really close right there. Okay. The other thing I want to show you is when we're at 9 years, that means that the cost is $4,611. So the car costs that much and that's how much it costs to maintain. Okay, so that's the reason people sell their cars when they're a little younger. I think that cost thing is a little off, but I won't judge right now. So using Desmos, we found out that it was at about 9 years, and we found out that at 9 years the value of the car and the cost of the car was about 4,611. Okay, good. This page is a good summary, and if you still have some room on page 125 that you haven't already used, this would be a good thing to put on there, okay? So it talks about exponential growth and what exponential growth looks like, and you can see that it's addition, okay? And then it just shows you with real numbers in. Here's the growth rate. That means this is my growth factor because I took 1 plus 0.5, and a growth, of course, is going to go up. So it's going to go up like this. If I look at my exponential decay, look at that right there. It's going down, so I'm going to subtract, and it shows all that same thing. And of course, an exponential decay is going to come down. Now you'll notice on all these problems so far, well, that will come up, I believe. Hold on. Well, just in case, think about the asymptote in a growth and decay. Okay, an asymptote in a growth and decay. Remember, this is where it's a line where the graph approaches. Well, if you think about most of these things, they're not going to go below zero anything because we're talking about real world. So I can't have I could have a population that goes to below zero. Nope, they just have to go to zero. Okay, I could have a car that depreciates all the way down to zero, but it's not going to be a negative amount. Well, we won't get into that too much. But anyway, you can see my asymptote on these is going to be y is equal to 0. Let's talk about what kinds, so essential question number 1, I'm now on page 126. What kind of situations can be modeled with growth? If I think about growth, okay, we can think about population. And you'll notice in your book, there's also about investments. Those can be exponential also. We can talk about cells having, so if I'm talking about in a petri dish and I'm looking under a microscope, they can explode. Heck, COVID, so viruses, and we got to live through one. A virus is an exponential growth. Now, an exponential decay is going to be depreciation. So your car depreciates, and a lot of things that you buy. Depreciation. Okay, that's one. We can have a car depreciate. We can look at the number of viewers that are interested. That is a depreciation. We can talk about cells in a petri dish. Okay, so there's different ways. Anything that decreases is decay. Anything that increases is growth. Look at number 3. Latanya says the growth factor is 25%. What mistake did Latanya make? Okay, well remember the growth factor is right here. The growth rate is 25%. Since it's a growth, we know that it's 1 plus the rate. So my rate, she mistake factor for rate. This is a rate. This is the factor. So the factor is 1.25. The rate is 25%. And number 4, why is the growth factor 1 plus r for an exponential function growth? Why is this the growth factor? Because it's going up. And this correct answer that the book gave was such a good one, I just wanted to show it to you. The growth factor is the b term in the exponential function. We already talked about that, where it's a growth, and b has to be greater than 1. Okay, so it talks about 25%, therefore you multiply by 1. But it has to be 1 plus the rate because it's a growth. It's going to happen, plus it's going to grow. So this is it happens, and this is how it grows. The r is where it grows. Okay, good. We're still on page 126, and on 126 this is number 5, and we're just going to practice writing out growth and decay functions right here. So first thing you're going to have to do is identify, is it a growth or a decay? So let's read it. Write an exponential growth or decay for the situation with an initial value of 100 increasing at a rate of 5%. Well, it's increasing, so that means that it's a growth. It's an exponential growth. So let's write out exponential growth. F of x is equal to a times 1 plus r to the x. So what's the initial value? Remember, a is the initial value. That's 100. And then we have a rate of 5%, so that moved my decimal point 2 places. And if I move it 2 places, that's 0.05, so that's 1 plus 0.05. So therefore, f of x is equal to 100 times 1.05 to the x. And I know some of your brains out there are going, well, can't I just put 1.5 since it's a growth? I know that's what it's going to be. Yes, but my job is to teach you how to get there. So yes, you could go to that. So try number 6 right now. Go. So on this one, again, we're increasing, so it's going to be a growth. So I'm going to add, and I'm going to get 1,250 times 1.25 to the x. Go to the next one. On number 7, write an exponential growth or decay for a situation with an initial value of 512 decreasing at a rate of 50%. So we know this is a decay. If it's a decay, it's going to be f of x is equal to a times 1 minus r to the x. So let's fill that in now. So I begin with 512. I'm going to take 1 minus. Now 50% is 0.50. So I'm going to have 1 minus 0.50 to the x, which is going to give me that f of x is equal to 512 times 0.50 to the x. Good. You try 8, go. So hope you recognize the words decreasing. So it's going to be a decay. We know our initial amount is 10,000. So we're going to take that times 1 minus. And when you have decay, I'd be very careful. This is going to be minus 0.12 to the x. That's the reason I always write it out. It's just one extra little step. Takes me like 10 seconds more to go from this equation to this one. So if I write it out, I'm less likely to make mistakes. So this is 10,000 times 0.88 to the x power. Okay, so there are our notes for 6.3. Please go out and work on 6.3, practice 6.3. Find that in Schoology. Thank you very much, and if you have questions, you know where to find us.